We're starting a new chapter today. You'll remember that I told you that Chapter 8 was a bridge between mechanics, which was the first half of the year, and energy, which will be largely what we'll be talking about in the last part of this year. And we're going to start with thermal energy. We already had a conversation about it in the last chapter. We're going to expand our view of thermal energy beyond thermal energy that is created strictly by friction. And the chapter will cover thermal energy, temperature, and heat. Temperature, you kind of already understand, is different than thermal energy and heat. But you'll hear people use thermal energy and heat as though they are the same idea. And in most cases, it really doesn't matter. They're so similar that it is an interchangeable idea. But in this chapter, you're going to hear how they are different and where the distinction is made. So let's start with thermal energy, the one that's already familiar to you. Thermal energy is the sum of the random motion. You already knew this from the last chapter. I'm just repeating it for you. The random motions of the particles. And by particles, I mean subatomic particles, or atomic particles like atoms, molecules, formula units, ions. And by the sum of the random motion, I actually mean the sum of the kinetic energies. So the different types of motions we've talked about before, the first one is translational. And I keep bringing this up because these types of motions show up so much in what we talk about. It shows up in kinematics, it shows up in thermal energy, it shows up in rotational motion, it shows up all the time. So it's the translational motion, which would be from A to B. And there's two types of translational motion, either in a straight line or in a curved line. I don't really care. We're just going to group them together as translational from point A to point B. The next one is vibrational, which you'll remember vibrational is back and forth across the center line. And do you remember what the last one is? The last one is rotational. Rotational is spinning on an axis. And all of those are what happens in molecular motion. They're all potential for what could happen in molecular motion. And axis, there we go. And just so you get a sense that, it's not just this lazy kind of motion, but specifically with gases, motion changes 1 times 10 to the 14 times. 1 times 10 to the 14 times per second. It changes direction because of collisions. So this is not just they're lazily going down a river. They are bouncing into each other and moving off super fast and bouncing again. They're changing their direction that many times in a second, which almost seems unbelievable, but that is true. As the substance becomes hotter, molecules translate, and you've heard this before. Molecules don't get hotter, they get faster, but let's be specific. They translate, vibrate, and rotate faster. Molecules don't get hotter, they get faster. And in the getting faster, they get faster in all forms of their motion, translational, vibrational, and rotational. All right, so thermal energy is the sum of the random motion, or the sum of all of the kinetic energy, be it translational, vibrational, rotational, of all of the particles in a substance. Temperature indicates the average. And you'll notice that we're talking about some math terms here. It's not the sum of the kinetic energy, it's the average kinetic energy of all the particles in a substance. And you already know this, or you would, it's intuitive for you to know this, as temperature increases, so does thermal energy. It increases as well. They are tied to each other because I can't increase the random motion of all of the particles without also increasing the average motion of all of the particles. The two concepts go hand in hand. But note that temperature is average per molecule and E thermal is sum. Temperature is the average kinetic energy per molecule, and thermal energy is the sum of the kinetic energy of all the particles. Okay, and I'm going to have you step back a little bit, and I want you to think for a moment which has more thermal energy. A teaspoon of boiling water or a bathtub full of room temperature water. Which has more thermal energy? A teaspoon of boiling water or a bathtub full, a teaspoon, I don't like that. Let's change that, okay? Which has more thermal energy? Because it's just kind of hard for you maybe to visualize how much a teaspoon is if you're not accustomed to it. Which has more thermal energy, a cup of boiling water or a bathtub of room temperature water? I want you to stop and I want you to pause the video for a little bit. And I want you to give that some thought, and I want you to have an answer for what you think, or I want you to have an answer for it, but I also want you to give me a reason for the answer that you have. And the next day, I'm going to ask you guys in our Zoom time to explain to me what you think the answer is and why you think it was that answer. All right, so let's move on to the next piece of it. And let's talk about how a thermometer works. A thermometer obviously is the tool that measures the average kinetic energy. It indicates it. It's not measuring it in terms of, well, the average kinetic energy is X number of meters per second, but it's an indication of the average kinetic energy. A thermometer works because of a principle called the fundamental thermometric property. Fundamental thermometric, I got all that on that line, I'm proud of myself. The fundamental thermometric property, which basically says that, and this is not universally true, but for what we use for a thermometer, it is going to be true. It basically says that as a substance warms, it increases in length or volume. As a substance warms, it increases in length and volume. And I say not everything does it proportionally like it has to be and consistently like it has to be for a thermometer. All right, temperature scales are based on, and I want you to pause the video here and I want you to stop and think. If I were to hand you a tube and just say to you, okay, I want you to develop your own temperature scale. Stop and think what that would require. In order for me to have actual degrees, what is the very first thing that I need? I need 2 fixed points, and at least 2 fixed points, but usually it's 2 fixed points. I need at least 2 fixed points. Those are going to be, you're going to mark them. You're actually going to take your thermometer and you're going to establish what that fixed point is, and then make the thermometer whatever you want the number to be at that fixed point. So, for example, with the Celsius scale, do you know what the fixed points were for the Celsius scale? What are the two numbers that come to mind right away for the Celsius scale? I'm sure you're thinking that the two numbers would be 0 degrees Celsius and 100 degrees Celsius. The two fixed points were the freezing and boiling points of water. The freezing point and boiling point of water, which obviously are 0 degrees and 100 degrees respectively, and degrees Celsius, of course, respectively. So literally they just, and it has to be at the proper pressure as well, but literally they just took this thermometer that wasn't marked at all yet, had, I'm sure at that point it was mercury, now we use alcohol, but you put it in in freezing water, right where water is at the freezing point, and you put the thermometer in there, and you just let the thermometer get to a point where it is stabilized. And you mark that on the thermometer. You make a little hash mark on the thermometer. Then you take the thermometer out and you put it in boiling water. You let the mercury rise until it hits the very highest it's going to get while it's boiling. And you mark that point as well. And if you decide that it's 0 and 100, then you have to divide that length that you have created by those two hash marks into 100 equal points. That's how a thermometer is made. And for the Celsius, it was the freezing and boiling point of water, and then they divided it into 100 equal units. Okay, now what do you think of for Fahrenheit? Typically, you're going to think of 32 degrees Fahrenheit is freezing point and 212 degrees Fahrenheit is the boiling point, but those really, really feel random, don't they? There's a lot of stories about how this was actually developed by Fahrenheit. He was the guy that did that. He was from Holland, but he did his work in Denmark. And he came up with this idea, and again, there's a lot of stories about this, so I'm just picking one of the stories. But he decided to use the fixed points at a time when it was a record-setting cold winter, record-setting. And he thought, okay, this is the time to create this scale. So he would take his thermometer out and leave it outside, and he would keep an eye on it. And every time it would go a little lower, he'd make a hash mark. And every time it would go a little lower, he'd make a hash mark until it was as low as it got. And he decided to call that 0 degrees Fahrenheit. So for him, it was the coldest it got, because it was record setting. They're thinking, all right, it's never going to get any colder than this. It got in Denmark that particular year, but again, a record-setting year, and he called that 0 degrees Fahrenheit. And he did that because he wanted a scale where he would not have to be working with negative temperatures. And for him, in what he did, that worked out just fine because it never got below that temperature in his lifetime. Like I said, it was record-setting cold winter. And so he thought, okay, I'm pretty safe in calling this 0 degrees Fahrenheit so that the work he did would never produce negative temperatures. And of course, you know in your work in chemistry, that's kind of important. But then, okay, so 0 degrees seems like the obvious one, and 100 degrees seems also like the obvious one. What would you say is super close to 100 degrees Fahrenheit? You're probably, I would think, you're probably thinking body temperature. What's weird is we say body temperature is 98.6. And so he used body temperature. So for us, it's 98.6, but he said body temperature was 100. So there's a little discrepancy there, but not a lot. Body temperature as 100 degrees Fahrenheit, and he marked that. He divided that into 100 equal units. Now, based on that, once he established that scale, put all the hash marks in there, then he put it in frozen, in ice water. And when he put it in ice water, he saw that now the temperature scale was up to 32 degrees. And then again, he put it in boiling water, and he had to extend his scale up higher to 212 degrees. But the units or the points, his fixed points that he used, was the coldest it ever got in Denmark and body temperature. And then from there, he developed the 32 and the 212. They were not the points he used. Those would be very, very random, just to sit at his desk and say, today I'm going to decide what my temperature scale is going to be. I'm going to make 32 degrees Fahrenheit water freezing, and let's call boiling water 212. That would be just silly. Instead, it was still the 0 and 100, but it was not based on water. It was based on how cold it got in Denmark and body temperature. The Kelvin scale is also called the absolute scale, and it's absolute scale because it has absolute 0. 0 is the theoretically lowest temperature possible. And you perhaps have heard that they have breached 0 Kelvin, but they've breached 0 Kelvin not in an actual temperature where all motion stops, but they've brought into it also the consideration of entropy, that it's not just about the motion, but it's also about the randomness or the disorganization. And so by bringing those two concepts together, they can call it 0 Kelvin, even though and they even breached it and said it was below 0 Kelvin because of that. That's kind of been talked about a lot since it's happened, that it's not really that it was below 0 Kelvin. It's more of a theoretical, even a philosophical approach to what temperature measures. So we're still safe in saying, yep, absolute 0, lowest temperature possible, we're good with this. And it is based on the Celsius scale. So it's the same size as the Celsius scale in terms of 1 Kelvin is equal in size. If I change 1 Kelvin, it's equal to change 1 degree Celsius. Notice I don't use degrees for Kelvin. It's just not done. It's not that important, but it's not done. So if I go from 4 degrees Kelvin to 6 degrees Kelvin, it would be, let me do it in ways that it's easier. It would be the same difference in temperature as if I went from 10 degrees Celsius to 12 degrees Celsius. My scale is the same size scale. Degrees are the same for Celsius and Kelvin in terms of the size of them. All right, let's just look real quick at the conversions that we have here. You've worked with these probably since you were in elementary or middle school. Here are your conversion formulas. Just keep those in front of you while you're working on some of these problems. All right, let's just do a couple of these problems. And the first one is going to be 9.1, which says if the temperature in the room is 20 degrees Celsius, what is it in degrees Fahrenheit? And this is just a nice straight up conversion formula here. So my degrees Celsius is equal to 20, and I just need to know what is my temperature in degrees Fahrenheit. It's just a quick application of F is equal to 9/5 Celsius plus 32, which is the same as 9/5 times 20 plus 32. And you end up with 68 degrees Fahrenheit. And I kind of wanted to do this one in particular because it's numbers that you can kind of get a sense of. If I'm talking about 68 degrees Fahrenheit, that is room temperature. maybe a little bit colder for some of you, but it's room temperature. My classroom is usually between 69 and 70 degrees. So this would be really close to what the temperature in my classroom is. In countries that use the metric system, then this would be what typical room temperature would be. 20 degrees Celsius is more close to room temperature. So you really get a sense of how different those are. All right, let's do the next one. The next one is the normal core temperature of the body is 98.6 degrees Fahrenheit. What is it in degrees Celsius? And let's go ahead and set this up. So my Fahrenheit is equal to 98.6 degrees. 90, I don't know why I put that in there. Let me get rid of that. We'll try that again. My Fahrenheit is equal to 98.6 degrees. And I want to know what is it in degrees Celsius. So I'm going to use my other formula, which is Celsius is equal to 5/9, parentheses, Fahrenheit minus 32. And I hope I got that right. I'm going to double check that because I'm not sure. Yep, I did. Okay, minus 32. And so I'm going to plug in that it is 5/9 times 98.6 minus 32. And when you do the math on that, you end up getting 37 degrees Celsius. And you're going to find that the reason it's not a really simple formula is because the sizes of the degrees are so different. Degree Fahrenheit is much, much smaller in temperature change or in change in how it feels than degrees Celsius is. So you have to have kind of a funky conversion formula for it in order to get a sense of this. And by the way, if we are going from, let's say that I give you Fahrenheit to Kelvin, then of course you know that you would just go from Fahrenheit to Celsius, Celsius to Kelvin, or backwards. I mean, you're just going to have to go that in between if you need to go from one to the other. All right, your homework is going to be number 1 through 7. And be careful with number 6. Your first inclination might not be the right one. So I just want you to remember delta T is equal to T minus T naught. Keep that in mind for number 6, and hopefully that will